My dear children, welcome back to episode 37 of Decode NCERT. So today in this session we are going to decode the chapter D and F block elements. Okay, so you know this is one of the very theoretical and very I can say rote memory type of chapter. So yes, I'll be telling you all the important things that you have there in this particular chapter. You need to mark it down and you need to study these particular points before your exam. Okay, so you need to focus on these points. Let's get started here. So yes, let me zoom out. Yes, okay, now you can see here, first of all you will be talking about the position of the D block element. Okay, so here it is, I have highlighted group number 3 to 12 and there are D block elements 4F and 5F. Next we have what is transition metals and inner transition metals. And then here different series are given. Okay, 3D starts from scandium to zinc, 4D is from Y to CD, FD2 is from lanthanum and then HF to Hg, 6D is starting from actinium and then elements from RF to Cn. And these inner transition elements, that is 4F, 5F, are known as lanthanoids and actinoids respectively. So what you have to remember exactly here, the series and the starting element and the last element. Okay. Next, coming to the definition of transition elements. What are the transition elements? What is its definition? That is, they should have incompletely filled d orbitals. Okay, and zinc, cadmium and mercury are called as the okay, they are not registered as transition metals, but they are studied with transition metals because of their similarity in the properties. Okay, so that is all. Next we will go to the general electronic configuration n-1d 1 to 10, ns 1 to 2. Okay, but here there is something very important except for palladium. Okay, palladium doesn't have this electronic configuration and its electronic configuration is 4d10 5s0. So please remember this one, again very important thing. Now chromium and copper has different electronic configuration. We all know that because of fully filled and half filled configuration. Now if we move forward and then we go to the yes, now what is about zinc, cadmium and mercury? The general formula is n-1d 10 and ns2. Now because they have they are not considered as transition elements because they have fully filled d orbitals in the both common oxidation state as well as in the ground state. Okay, now next here nothing important is there, then you can move directly to their properties. So what are the metallic properties they have? High tensile strength, ductility, malleability, high thermal and electrical conductivity and metallic luster. Okay, and what are the exceptions? Zinc, cadmium, mercury and manganese, they have only like other, except these they have one or more typical metallic structures. You can see here that metallic structures are given. This you may not be able to understand because it was there in your solids chapter, which is deleted right now. Okay, now coming to the other properties here, the first one, the transition metals are generally very hard, have low volatility and have high melting and boiling point. What are the exceptions here? Zinc, cadmium and mercury. Next, why they are having this high melting point? Because of strong interatomic bonding. Okay, next we have manganese and technetium and okay, so in this what happens, the value of magnesium, technetium is generally very low. Okay, that is there. Then their metals have high enthalpies of atomization. Okay, so these are some properties that you should know. Next we have second and third series greater enthalpies of atomization than the corresponding elements of the first element. So as we go down the group, the enthalpies of atomization increases. Okay. Next, here we have about the atomic size. It decreases in radius along with the increasing atomic number. So along the period what happens, that is given here. Next, this is important, that is when the atomic sizes of one series are compared with those of the corresponding elements in the other series. Okay, so the curve in figure 8.3 shows an increase from the first to second series of the elements, but the radius of the third series are virtually the same as those of the corresponding members of the second series. This phenomenon is called as, or because of, lanthanide contraction, which happens due to the poor shielding effect of 4f orbital. Example, zirconium and hafnium. You can see the graph here, 3D, 4D and 5D sizes are almost similar. Okay, next what happens, this is because of imperfect shielding of the 4f electrons. Now you can see because of the increase in mass and decrease in radius, the density of the elements along the period increases. Okay, next let us see what we have ionization enthalpy, left to right, what happens? The ionization enthalpy increases in nuclear charge because of the increase in effective nuclear charge. Okay. Next we have a question here. What happens? The ionization enthalpy increases slightly in the 3D series. So if you go from left to right, the ionization enthalpy increases, but the rate of increase is very slow. What is the reason for that? You have to explain here. See, the nuclear charge increases from scandium to zinc, but electrons are added to the orbital of inner subshell, that is 3D orbitals. These 3D electrons shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. So 3D is there, 4s is there, right? So 3D electrons can shield the 4s electrons. So that is why what happens? The effective nuclear charge is less. Therefore, the atomic radius decreases less rapidly. Okay. Now, a general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases, because one d electron does not shield another d electron from the influence of the nuclear charge, because d orbitals differ in the directions. So second ionization enthalpy, when you talk, okay, so that means what? The second ionization enthalpy, the d electrons which is present inside the orbital, okay, in the inner orbitals, they do not shield each other much effectively, because they are in the other different directions. So that is why the second enthalpy or the second ionization energy has a higher value. Okay. Next, you can see compare Mn2 plus and Fe3 plus D5 configuration. So they will have higher enthalpy of this one. So what factors the ionization energy depends? Repulsion between the electrons, exchange energy, and the attraction between the electrons and the nucleus. What is exchange energy? It is the measure of the stabilization of the energy state, and it is approximately equal to the total number of possible pairs of parallel spins in the degenerate orbitals. How many parallel spins you can have, that many amount of exchange energy will be there. Okay. Next we can see here the ionization enthalpy of Mn plus is lower than that of Cr plus, because yes, Mn plus, if you remove one electron, we will get D5 configuration, right? Similarly, Fe2 plus is lower than Mn, because if you remove one electron, we will again get D5 configuration here. Now what is the lowest common oxidation state of these metals? It is +2. Okay. Next we have third ionization enthalpy of copper, nickel and zinc indicate that it is too difficult to obtain the oxidation state greater than 2 for these elements. Okay. Now if you see talking about oxidation states, okay, in the middle of the series the element have the highest number of oxidation state. You can see from manganese has oxidation state of +2 to +7, and towards the extreme end they have very less number of oxidation state. So you can see like scandium and titanium, or too many d electrons, where copper and zinc, they have less number of oxidation states. Okay. Now one more thing about oxidation state is titanium +4 is more stable than titanium +3 or +2. Okay. At the other end, the only oxidation of zinc is +2. Okay. The sum, so what happens generally up to manganese, the highest number of oxidation state is equal to the group number of the element. This question was there in the midterm paper of Bangalore South. Okay. Now why so many oxidation states are there? That is because of the incomplete filling of d orbitals. Okay, now one more interesting fact here, that in non-transition elements lower oxidation states are more stable, but in transition elements the higher oxidation states are more stable. So you can see molybdenum in +6 and W +6 are found to be more stable than chromium +6. Okay, so in the non-transition elements what happens, down the group lower oxidation states are more stable. But if you see here, we have chromium, molybdenum and tungsten, right? So molybdenum and tungsten in +6 states are more stable. So the chromium in +6 state in the form of dichromate in acidic medium is a strong oxidizing agent, whereas MO in +3 and WO3 are not. Okay. Next we have low oxidation states are found when there is a pi acceptor ligand. So you can see NiCO4, FeCO5, they have 0 oxidation state. Next, coming to the trend in M +2 to M. So copper have a positive E0 value. Okay, what is the reason for that? Because of high second ionization enthalpy. Okay, and but along the period generally what happens? It goes less negative. The E0 value becomes less negative along the period. Okay, now here we have something. E0 for manganese, nickel and zinc are more negative than their expected value. What is the reason for that is also given. So you can see the reason for Mn2 plus is its half filled stable configuration, Zn has fully filled D10 configuration, but for nickel the reason is highest negative hydration enthalpy. Okay, this you should mark. Next we have this is M plus 3 to M plus 2. This I have explained very well in my lecture. You can see if there is half filled configuration, then definitely E0 value will be less. If it is going from stable to unstable, then E0 value will be high, E0 value will be low, and if it is going from unstable to stable, the E0 value will be high. Well, how we talk about stable and unstable? Based on their D10 and D5 configuration. Now if you talk about higher oxidation state, the plus 7 state is okay, once the fluorine can stabilize the plus 7 oxidation state because of either its high lattice energy in presence of, as in case of COF3, or its high bond enthalpy as in case of VF5 or CRF6. Okay, so it has high bond enthalpy and higher lattice energy. Next, similarly we have here disproportionation reaction of copper. This is also a very important question. Then the stability of Cu2 plus is more stable than Cu plus because of its hydration energy. Okay, now if you see that oxygen has more tendency to stabilize the higher oxidation state because of its ability to form multiple bonds. Okay, next if I see okay, so coming to the E0 values, an examination of the E0 values of the redox couple M plus 3 to M plus 2 shows that M plus 3 and CO plus 3 are the strongest oxidizing agents in aqueous solution. Strongest oxidizing agent means they will undergo reduction. So if it undergoes reduction, plus 3 to plus 2, it will gain stability. So that is why this one will undergo reduction. The ions Ti2 plus, V2 plus and Cr2 plus are strong reducing agents and will liberate hydrogen with dilute acid. Okay, so this reaction is given to you. Next, here we have magnetic properties, diamagnetic, paramagnetic, and we have what is ferromagnetic. And the formula to calculate the magnetic moment is important. Unit should be there, Bohr magneton. Okay, and okay, so here the number of unpaired electrons and the magnetic moment. So this you already know the formula, you can calculate. Then colored compounds is because of DD transition, we all know that. Then moving to complex compounds. So what is the reason for forming complex compounds? That is due to comparatively smaller size of the metals, ions, high ionic charges, and the availability of the d orbital for bond formation. So 3 points, it can be easily a 3-marker question. So make sure that you learn this. Next, catalytic property. Catalytic property examples are given, so many examples are there. So what is the reason why they show catalytic property? Ability to adopt multiple oxidation states and to form complexes. Now what are the examples? See, vanadium is used in contact process, iron is used in Haber's process, nickel is used in hydrogenation, and some of the other examples. Okay, so here some examples are given of iron, how it catalyzes the reaction between S2O8 and I minus. Okay. Next, what are interstitial compounds? So when small atoms are present, so this is the definition of interstitial compound. This is the example, so you should be knowing the examples and what are the properties of the interstitial compounds. Next, alloy formation. So what is alloy formation? Mixture of metals. Examples are given, copper, zinc, brass, bronze, aluminium. So these all examples you should remember. Now coming forward to oxides. Okay, so here oxides are generally ionic in nature, okay, except scandium form MO oxides which are ionic in nature. Okay, now as the oxidation number increases, the ionic character decreases. So you can see here, as the oxidation number of a metal increases, the ionic character decreases. In case of manganese, Mn2O7 is a covalent green oil. Okay, so you remember the color, and the acidic character is predominant. So here you see higher oxidation states, it will be acidic in nature. Here examples are there, V2O3, V2O4 are basic, V2O5 is amphoteric. Then you have here CRO is basic but C2O3 is amphoteric. Next you have potassium dichromate reactions, the preparations of potassium dichromate, 3 reactions, very important. Then its acidic and basic medium conversion, this is important. Then you have the oxidizing nature of potassium dichromate. These reactions are important. Potassium permanganate, the preparation method, but here something is important is your commercial method, right? So you should know which one. If the question is asked, write the commercial method of preparation of potassium permanganate, then you should write this particular second method. Okay. Now moving forward, we have again the oxidizing nature of this one. KMnO4 can get decomposed, okay, then it is paramagnetic, and here we have the oxidizing reactions of permanganate ion. So next, this is in so this is in your neutral medium, acidic medium and basic medium. What are the reactions that is given? Then the oxidizing nature in acidic solution, okay, these all reactions you should understand. Yes, so next is very important here, permanganate titrations in the presence of hydrochloric acid is unsatisfactory because permanganate ions oxidizes hydrochloric acid to chlorine gas. Okay. Next we have inner transition metal, so nothing much important here. So again, what is lanthanide contraction? We have already studied that. So next, this size is given, that is also there. Now the oxidation state of lanthanides is generally +3, okay, but they can also show +2 and +4. So examples are there which can show +2 and when they will show. So for example, cerium can show +4 to you, okay, then Pr, Nd, Tb and Dy can also show +4, okay, Eu shows +2, okay, then you have Yb shows +2. So these are the elements which can show +2 and +4 oxidation state, you should remember, okay. Generally it is +3, but some elements can show +4 and +2 as well. Next we have here general characteristics. So the samarium has a higher melting point, that you should remember. Then they do not show any color, La3 plus and Lu3 plus, due to the unpaired absence of unpaired electron. Okay. Next, these reactions of lanthanoids are given, just have a glance on this, but questions are not much asked from this part. Okay. Next, mic metal is very important, questions can be asked from here. The composition also you should remember, 95% of lanthanoids and iron contains 5%, and you have traces of sodium, carbon, calcium and aluminium. Okay, and it is used in what? Magnesium based alloy to produce bullets, shell and lighter flint. Okay. Next, lanthanum oxides are also used in fluorescing screens or surfaces. Now coming to actinoids, not much. So why they are very difficult to study? Because they are radioactive, they have shorter half-life and they are produced in nanogram quantities. Next, coming to electronic configuration, AM and CM are 5f7 and 7s2 and 5f7 6d1 and 7s2 configurations. Okay. Next, what is actinide contraction? Just like lanthanide contraction, but actinoid contraction is much more greater than lanthanide contraction due to the poor shielding effect of 5f electrons. Now coming to oxidation state, what you should be knowing? They have greater oxidation states because of the similar energy of 5f, 6d and 7s orbital. Okay. Now the maximum oxidation state increases from +4 in thorium to +5, +6 and +7 respectively in Pa, U and Np, but decreases in the succeeding element. So you should know the highest oxidation state is Np of +7. Okay. Next, we have here general characteristics, you can just go through it, not much important part. Okay. Yes, application based is very important here. So TiO is used in pigment industry, MnO2 is used in dry batteries and also is required for zinc and nickel cadmium. Okay, this is also important. Next, we have something here which from where questions can be asked. UK copper coins are copper coated steel, silver UK coins are a copper nickel alloy. Okay, so this is very potential question. Then what is V2O5? It is used in the oxidation of SO2 in the manufacture of sulfuric acid. TiCl4 with AlCH3 forms the basis of Ziegler-Nattler catalyst. So this is can also be asked. All this important part is which metal is used in which catalyst and what is the function of that catalyst. So for example, Ziegler-Nattler is used for polymerization. Iron catalysts are used in Haber's process. Nickel catalysts are used in the hydrogenation process. Wecker's process, the oxidation of ethine to ethanol is used. Okay. Next, Nickel complexes are useful in the polymerization of alkynes and other organic compounds such as benzene. Now also AgBr is used in the photographic films. Okay. Now apart from these important points, you should also focus on the I'll say in-text questions and solved examples for this particular chapter. Okay, they are very important, and these are the basic things that you should be knowing, and just do more questions from this particular chapter. That will be enough. Okay, so that's all students in this class, and I hope that this video would have helped you. You would have underlined all the important points, and please revise accordingly. Okay, thank you, and do not forget to subscribe the channel, and see you soon in the next class.